artificial intelligence is not limited to machine learning. Another fundamental area is automated reasoning, which is the attempt by researchers and engineers to reproduce in machines one of the most distinctive abilities of human beings: the ability to explain the reasons behind things, to identify causal relationships between events and phenomena. Reasoning is based on a top-down approach, where rules that describe how a system works are defined in advance. Then these rules are applied to generate answers, predictions, or decisions. However, this approach has a significant drawback. When the complexity of the system increases, for example, the number of variables involved, the number of rules to consider grows exponentially. As a result, the time needed to calculate a response also increases, making the process slower and less efficient. The first developments in artificial intelligence date back to the 1950s and 1960s, when researchers tried to reproduce human thought through logical and symbolic rules. This approach, known as good old-fashioned artificial intelligence, was based on the idea that intelligence could be achieved by explicitly programming machines with a set of rules and knowledge. Expert systems, developed mainly between the 70s and 80s, represent one of the most emblematic applications of this vision. They were designed to emulate the decision-making process of a human expert in specific domains, like medicine or engineering, using a knowledge base and an inference engine. These systems were able to provide detailed answers and logical explanations, but they had significant limitations. Their effectiveness depended heavily on the completeness and accuracy of the rules provided. And maintaining the knowledge bases quickly became complex as the number of variables increased. Moreover, they were not very flexible. They didn't learn from data, but relied exclusively on what had been programmed. Nevertheless, good old-fashioned and AI laid the theoretical foundations for many of today's technologies. And the topic of automated reasoning is still central today in many areas of artificial intelligence. Let's look at an example of these tools in modern navigation systems, where artificial intelligence plays a crucial role in optimizing routes, offering users the best route or routes based on variables such as travel time, distance, traffic, or personal preferences. One of the most well-known and widely used algorithms for this purpose is called A*, which calculates the most efficient path between 2 points, taking into account both the cost already incurred, for example, the distance traveled, and a heuristic estimate of the remaining cost. From a theoretical point of view, this type of artificial intelligence embodies several key principles of intelligent optimization. Causality, because it can explain the choices made, for example, choosing the fastest route due to an accident on the main road. Explainability, because the user can view alternatives and the reasons behind them. Optimality, because the system always seeks the most efficient solution based on the established criteria. And adaptability, because it updates in real time in response to new conditions. However, these advantages are based on a fundamental assumption. The programs must be correct, reliable, and scalable. And it's precisely with scalability that the main limitations of classic algorithms like A* emerge. When the number of nodes, that is, the number of roads, intersections, or detours, increases, as happens in complex road networks or high-density urban scenarios, the algorithm can become computationally inefficient, requiring too much time or memory to find an optimal solution. This makes it difficult to apply directly in large-scale contexts without additional simplifications or optimizations. In other words, although A* is theoretically elegant and precise, it doesn't scale well in dynamic and highly complex environments where more flexible and approximate approaches are preferred instead. Today, these algorithms are combined with machine learning techniques and constant real-time data analysis. In this way, the system is able to process millions of pieces of information from sensors, maps, traffic histories, and user reports to suggest the most efficient route in just a few seconds. In contrast, machine learning follows a bottom-up approach. It starts from the data and, through statistical analysis, builds a model that describes the observed system. This method makes it possible to achieve high performance within a specific domain, but it is strongly tied to the quality and quantity of the available data. Moreover, it has a significant limitation: the lack of causal explanations. In fact, while reasoning tries to explain why something happens, machine learning is limited to saying what is likely to happen. The answers provided by machine learning models are probabilistic, not deterministic. The system tells us that a certain event has a high probability of occurring, but it is not able to clearly explain the reason why. This opacity is one of the most discussed topics today, especially in relation to the transparency and reliability of artificial intelligence systems. An effective example of machine learning is represented by automatic image tagging algorithms. These are used in applications like search engines or social media to recognize and classify any objects contained within images. These systems, trained on millions of images, are able to identify elements such as faces, animals, food, or landscapes with great speed and accuracy. The main advantages of this approach are the high performance, which allows for processing large volumes of data in a short time, and the domain specialization, which makes it possible to achieve very accurate results. In specific contexts, for example, recognizing tumors in medical images or products in an e-commerce catalog. A practical application of what we've just described, accessible to everyone, is Google Photos, which uses advanced algorithms to automatically recognize objects, people, and places within images. Thanks to these systems, users can search through thousands of photos not only by date or geolocation, but also by typing in keywords like umbrella, dog, bicycle, or beach. The system is able to identify and group images that contain those objects, even if they haven't been manually tagged. This demonstrates the high performance and domain specialization of machine learning, which can handle enormous amounts of visual data quickly and accurately, greatly improving the user experience. However, even in this case, structural limitations of machine learning emerge. Moreover, the approach is probabilistic. The algorithm assigns labels based on the probability that an object is present, but it lacks semantic or contextual understanding. This can lead to errors. For example, a purebred dog like a Chihuahua might be mistaken for a blueberry muffin because of their visual similarity. Such episodes, although rare, highlight how these systems, while powerful, are not infallible and can produce misleading results. Especially in the presence of ambiguity or unrepresentative data,